So now that we know how those capacitors work, we want to see why do we add them inversely in series, but to get like normally in parallel. So if I have two circuits, I want to compare this one, where I have two capacitors in series, versus this one, where I have two capacitors in parallel. So let's look at the series. If I have a positive charge moving this way, we have a conventional current, it starts building up right here. That's going to induce this side to build up with negative charges from this wire, and since the negative charges are coming here, the positive charges will build up on this plate. And again, by induction, your negative charges will build up on this plate from this side. Now, whichever one of these is the weaker capacitor, let's say this one's 2 farads and this one's 4 farads, when this one builds up to full, that means it's pushing back against the battery and no more charge is moving here. So that means that no more charge is moving here because this one's fully charged, so we can't put any more charge on this plate. That means that this capacitor, even though it by itself it can hold more charge, it can't draw any charge from this side, so it's limited, it's stopped. And so that means this whole circuit was limited by the lowest capacitor. However, in this circuit, let's say this one's the 2 farad and this one's the 4 farad, we have our positive charges coming down, and let's say here we charge this one to full. All that means is that the loop here has stopped, but the charges can still keep going this way. They still have an alternate option, and they can go until they charge this one to full. And so see, in this case we had only enough charges to the limiting capacitor, whereas here we had enough charges until all of them were full, which is why this one would be a higher capacitance, because with the same voltage it could hold a higher charge. So we want to add these together, which would come out to be 6 farads, whereas since this one was limited, it was limited to a charge that was less than what would have been them on their own. So we add their inverses, so we do 1/2 plus 1/4 equals 3/4, and then the inverse of that would be 4/3 farads. So that's why in parallel we add them together, and in series we add them as inverses. Now, what I said earlier about that we have to have a resistor in this circuit because otherwise the wire will melt, that's what we have known as RC circuits. In an RC circuit, this R is the total resistance of the circuit, and C is the total capacitance. So it's not just one of them. You remember, you have to find the equivalent capacitance and resistance of the whole circuit to find what we call tau. I think this is the last thing she covered in your class. So tau is your time constant. Your time constant, now remember to write this down. Your time constant is the amount of time it takes to charge the capacitors of your circuit up to 63.2% of their max capacity. Now that number seems weird, but I'll explain it in a second, and the formulas regarding that will be more prevalent after your test. So how do we figure out what tau is? Tau is equal to the resistance of the circuit times the capacitance of the circuit. It's just RC. So we have various formulas for like these RC circuits. I'm going to explain them now just in case she tells you that they're going to be on the test. If they're not going to be on the test, don't even worry about this. We have a formula for charging a circuit known as little q, which is the charge of the circuit as a function of time. Like how long has the circuit been running. That's going to equal big Q, which is the maximum charge, times e to to the negative T over RC. So this is your charge as a function of time equals the full charge times e to this exponent. So T right here is your dependent variable and Q is your independent variable. Sorry, other way around. T is your independent and Q is your dependent. So if we have a graph, we have Q versus T, and we have, so it's going to start charging really quickly because the capacitor is not fighting back the battery. And as the capacitor is gaining charge, it gets harder and harder to charge it, right? Because it's pushing back. So eventually it's going to level off at the maximum charge. It's going to level off at big Q. And so now, if we plug in tau for T, which is equal to RC, that's going to give us some point about right here, where this is 63.2% of Q. Now let's plug it in and do the math. So we'll get Q of T equals big Q times e to negative RC over RC, which is, so we divide by Q, and so we'll get little q over big Q is equal to e to the negative 1, which just equals 1 over e. And so you can see that, let's say 63.2% of Q we plug in for little q. 63.2% of big Q over big Q equals 1 over e, cancel. And so that's how we got that number. Basically 1 over e is 63.2%. So now just other conceptual things we want to think about with capacitors. A capacitor in a circuit, let's say we have one here. Let's make these light bulbs. Alright, and we have a switch right here that's open. So this is our battery, capacitor, and resistors that are light bulbs. So now initially this switch is open, which just means we only have one loop right here. So we just have a normal battery, light bulb, and that's going to be running at a certain current. Now, when we close this switch, initially a capacitor just acts like nothing's there because it has no charge built up and it's not fighting the battery. So we close it, and we're gonna imagine. So if you can have a question like, what happens initially? Just pretend like it's not there. Calculate the circuit. You have this resistor now in play. So you have these two in parallel, and then this in series with the combination of these. And if you remember, resistors in parallel go down. So we have the resistance of this was lowered, and this was the same as before, which means that we're going to have a lower resistance overall than before. Again, to repeat, because this resistor was added to this in parallel with the closing of this switch, the resistance there is lower than just this one before. And this did not change. So the total resistance of the circuit went down, which means the current went up. So these bulbs are going to appear brighter initially. Now, we have charge start to build up on this capacitor. Over time, so you have the question of what happens initially and what happens after a long period of time. After a long period of time, this capacitor is going to be fighting this battery at an equal strength of the voltage that would pass through here. So, no charges will be able to move this way. So we're back to only having the one option of coming down. And so now we only have this one loop again, which means no charges are flowing through here. This light bulb has turned off. These two light bulbs are now the only circuit. And so it goes back to the original resistance, which was higher. So our current's going to be lower, which means these two bulbs will be dimmer then when you close this switch, and this bulb will be off. That's the answer for the long-term question. So I think that's about it, covering the capacitors, concepts, what can happen with capacitors, resistors, switches, what happens in the beginning, what happens in the end, along with tau and charging a capacitor. If you get to discharging a capacitor, it works the exact same way, but in reverse. You start full and it goes lower. I guess one last concept I can add is if you wonder what do we use capacitors for in real life, one really good example is we want a quick discharge. So in your camera, when you turn the flash on, it charges a capacitor, and then when you click, it discharges that capacitor really quickly, and that's your flash. And we want to do that as opposed to a battery, because a battery would keep running, whereas a capacitor we can just charge, discharge anytime we want it. And it's not going to affect the life of the capacitor. It's just going to charge and discharge every time. Whereas with batteries you need to replace them. So yeah, I think that's about it. If you have any other questions, feel free to email me. I hope this helped. Spread it to everyone in the class. But yeah, good luck on your test.